The Cross-CPP project gives cross-sectorial industries access to a huge amount of sensor data coming from high-volume products such as vehicles or smart buildings. The new information sources create new value, improving existing services and fostering creation of new cross-sectorial ones. Sensors in cars, buildings, and other cyber-physical products, or CPPs, are permanently on and produce invaluable data. Companies, such as Volkswagen with their cars or Siemens with smart buildings, benefit from the new opportunities and deliver better services for their customers. However, there is currently no brand-independent solution in place that would define a unified form of access to such data. It means that every service provider needs to negotiate many contracts and interfaces to process data shared by its owners. The project overcomes these issues by defining a unique ecosystem integrating data streams coming from various cyber-physical systems, especially in the automotive and smart building sectors. It pays particular attention to intersectorial data and services. In general, the Cross-CPP ecosystem can be separated into 3 pillars. They will be described in the next slides. And it is relevant to various types of stakeholders, especially CPP manufacturers and service providers that can benefit from the cross-sectorial data. The left pillar corresponds to data providers, CPP manufacturers. It comprises data harvesting and making CPP data from various industrial sectors available, transferring brand-specific data streams into the common CPP data model. The middle pillar consists of the Cross-CPP cloud storage and big data marketplace. The CPP cloud storage enables controlled access to CPP data from different sources. The CPP Big Data Marketplace offers support to service providers in the form of easy access and detection of needed data. It also includes an analytics toolbox enabling service providers to process and analyze CPP data streams in a flexible and efficient way. The right pillar is relevant for data customers. Service providers can use available CPP data from various products to create new services and to improve existing ones. The project brings various innovations. 3 key innovative aspects include definition of a standardized way to collect and provide data with the focus on privacy and security. Creation of a one-stop shop for the data and its analytics which simplifies the use of the data by service providers. Demonstration of many advantages of the developer ecosystem in the form of innovative cross-sectorial services by Volkswagen, Siemens, and Medialogix. Members of the user interest group will be able to validate the mechanisms to have full control over their valuable data as owners of relevant CPP data and the ease of defining new services employing the data. The Cross-CPP Common Industrial Data Model, or CIDM, harmonizes proprietary data and provides means of transforming it to a generally usable form. The Common Industrial Data Model was defined to simplify the data exchange between 2 key stakeholder groups: CPP data owners and providers of services employing the data. The design of the data model was based on a detailed analysis of the requirements of both the groups. They provided feedback in several iterations and verified the applicability of the final specification of the data model. Key requirements on the CIDM include its scalability, brand independence, and openness, as well as its ability to cope with the high diversity of IoT data, the support of various signal and measurement types, and the focus on data ownership transparency. Key concepts of the model include signals, channels, and data packages. Signals describe the type of physical phenomena and chemical quantities of CPP, including the name of the signal, the format, and unit. Data from CPPs needs to be pre-processed and aggregated conforming a measurement channel that includes one or more signals to be aggregated, the aggregation type, time series, histograms, etc., and the configuration of the aggregation. Data packages provide the actual data coming from a CPP, aggregated according to a measurement channel selected. CIDM signals usually correspond to sensor measurements or status information. The data format enables defining various signal types and other characteristics of the signals. To cope with potentially enormous amounts of data and, also, to reflect strict data privacy settings, the data model defines a data aggregation and downsampling level of measurement channels. For example, the data can be sent as aggregated time series, a histogram, or a geo-based histogram channel. A collection of the data corresponding to one measurement channel and relevant metadata is then referred to as a data package. Data packages are the basic blocks manipulated by the Cross-CPP data marketplace. They are stored and indexed and can be retrieved by means of the defined API functions. The physical data model is implemented in JSON. Signals and measurement channels corresponding to the vehicle and smart building data were defined in the Cross-CPP projects. OEMs from other sectors can easily extend the model by defining plugins for their specific areas. Service providers use the marketplace to specify their data needs in the form of requests, corresponding to service offers data owners can accept. They log in with the credentials given by the data market operator and can interact with the system. They can search the catalog of available signals, specify the data requests, browse responses to the requests and corresponding data transactions in the data wallet, and process the data by means of the analytics toolbox.
When thinking about the CPP data that could be used in a service, service providers can browse the data catalog and examine the signals that have been already defined and are available in the data marketplace. They can have a look at catalog details associated with signal definitions, and consider whether a particular signal is relevant to their needs.
When thinking about the CPP data that could be used in a service, service providers can browse the data catalog and examine the signals that have been already defined and are available in the data marketplace. They can have a look at catalog details associated with signal definitions, and consider whether a particular signal is relevant to their needs.
Data providers can also inspect the list of the data packages they sent to the marketplace.
The data discovery process enables exploring general information and statistics on available data, corresponding to the signals and channels of interest. Service providers select the channels and can specify various criteria as filters for the data packages a newly offered service would use. They can choose particular time period by setting the dates and duration filters, or specify a particular geographical area of interest, either by drawing a bounding box on the map, or choosing a country.
Data providers can also inspect the list of the data packages they sent to the marketplace.
By clicking on the Data Discovery button, they apply the defined filters and can explore the results in the form of general statistics, locations, and the channel, time, or data package distribution. If the given set of channels and specified filters correspond to the intended data request, the user can describe it in a form data owners will understand and specify the use of the data by other marketplace modules. Service providers finally create the data request, which is immediately visible to data owners. If the owners accept the request, relevant data packages become available to the service provider.
Data providers can also inspect the list of the data packages they sent to the marketplace.
Existing data requests and corresponding data packages can be explored in Data Wallet. Service providers can review individual data packages sent by data owners and examine their content, for example, in the map visualization or as a histogram. The Data Wallet also enables exploring global statistics and parameters of the data transactions corresponding to a data request. The following slides explain briefly the components of the Data Analytics Toolbox and its foreseen applications. The Analytics Toolbox is formed by several modules. They can be classified by their functionality and the way the data is processed, either in a continuous manner, as a streaming, or in batches. Let's go through main functions and use cases of each component. The first component is a library is for streaming data, the time series library. Time series are defined as series of data points indexed in a sequence of successive time steps. They are widely used in several disciplines of knowledge processing such as the weather forecast, stock market, or energy consumption predictions. The module counts with mathematical tools to detect drifts, or sudden changes in time series. Drifts are well-documented symptoms of relevant changes in the evolution of a system. The two graphs on the slide provide examples of drifts. When the time is around 100, there is a clear change in each of the signals. The module also includes 3 techniques to predict future values for given time series: ARIMA, decision trees, and a perceptron. The next slide shows an application of the detection of drifts and prediction of future values in time series. To provide a solution based on data, the provider must count with a data collection and tools to process that kind of data. Once data collection has taken place, the verification of a sensor's trustworthiness is critical, since any anomalous behavior directly compromises subsequent decision-making, and even the customer's security. In order to detect such undesirable behaviors in the data received from the marketplace, the drift detection functionality from the Analytics Toolbox is of significant interest. By quantifying how aggressively a sensor's signal fluctuates, it provides a highly interpretable measure of the amount of noisiness embedded in it. An output like the one presented in this image allows for a clear separation of reliable and anomalous signals, thus aiding in the identification of malfunctioning devices. The next module is the Trajectories Library. It works in the batch mode. The concept of trajectory is very simple. It is the path that a moving object follows in the space during a time. Trajectories can be expressed in many ways. In the toolbox, they are represented as a list of GPS positions and corresponding timestamps. The library specifically focuses on trajectories of vehicles, although probably could be extended to other types of trajectories. It collects different functionalities of interest when working with trajectories data, especially trajectories of vehicles. Interpolation refers to resampling the trajectories. This could be of interest if the trajectories contain missing data, due to tunnels for example. It is possible to compute 3 characteristics in the statistics module: the length of the trajectory, its average velocity and the duration. Clustering refers to the task of categorizing the data in such way that the elements that belong to one group, called cluster, are very similar among them, and the more difference, the better, to the elements of other groups. To perform this kind of classification, a similarity metric must be defined prior the clustering. The detection of anomalies enables the verification of the quality of the data, also it could lead to valuable insights of uncommon behaviors. The next slides show possible applications of the Trajectories Library. The clustering module is specifically designed for the treatment of GPS data. This process can be of interest for identifying groups of trajectories, which may in turn be related to different behaviors in the measurements made by the associated car's sensors. An output consisting in clearly distinguishable groups of trajectories would enable a more fine-grained assessment of the conditions associated to a particular cluster. Moreover, the Trajectories module output can be used to identify and filter out any anomalous coordinate in the data being used. Additionally, in case there is no clear replacement at hand for the detected outliers and it is intended to further inspect the correspondent trajectory, the Analytics Toolbox also provides an interpolation function with which to resample a given trajectory's coordinates. These functionalities allow to pre-process and manipulate data so that the minimum information possible is lost, making the input to any subsequent analysis process as accurate and reliable as possible. The Networks Library forms another component of the Data Analytics Toolbox. Complex networks refer to the discipline of the study of graphs. It is a young and active area of scientific research. Networks are formed by nodes and links, which are abstract representation of the elements of a system. Characterizing the representative graph of a system allows to inspect the relations among the elements of the system in a quantitative way. There are two types of functionalities. To create the network from specific data. Update the network, including in an on-live manner. Obtain some basic metrics that include but not limit to the diameter, node degree, and shortest paths. The following slides provide interesting applications of the Networks Library. To ensure reliability in a car's measurements and the associated information prompts offered to the user, it is crucial to account for any potential effect of the vehicle's surroundings on the different sensors it carries. To exemplify, suppose a customer requires a temperature report for a planned route, which requires the system to estimate the temperature in the associated area. However, it is known that a car's color can heavily affect the temperature measured by its sensors, with dark tones absorbing heat and bright ones reflecting it. Disregarding this fact can redound in imprecise measurements being offered to a customer. In this scenario, the network's functionality from the Analytics Toolbox is a suitable option to clearly identify groups of temperature measurements on a specific area for the signals gathered from a Datagora's data request. By providing these as input, this procedure would generate a network in which highly related signals would be represented as a connected neighborhood. In this case, each group would represent the different temperature levels measured by different vehicles in the same area. Knowing beforehand the color of each of the cars involved, an information that is also available in Datagora, an output like the one presented in this image would reveal clear patterns on the temperatures measured by each type, thus allowing for a more accurate estimation of what the real value would be like, e.g. by computing a mean or any other summary statistic. Additionally, this functionality can also serve in anomaly detection. In the figure, anomalous temperature levels would be represented as a populated neighborhood lying further away from the others, and with no connections to them. This output is valuable in determining whether a customer's planned route comprises areas with weather conditions that need a warning to be prompted, since the car's signal would be related to an anomalous group in the resulting network. The last module of the Data Analytics Toolbox provides a generic interface for building advanced machine learning models from large data. It interconnects the marketplace with existing frameworks. Scikit-learn, TensorFlow, and PyTorch. The component distinguishes operations performed with a batch of data collected in the marketplace and streaming functions processing data as they appear in the system. There are also functions common for both the batch and the streaming mode, for checking the status of a running operation, exporting and importing the models, etc. Streaming machine learning services read data feed inputs and generate their outputs to data stream channels. To build a model from a stream of data, incremental machine learning methods need to be employed. On the other hand, the model application to a data stream can use model built by a batch or a streaming process. The discussed machine learning components were used to create prediction and classification models for two applications. A model predicting the use of Siemens e-chargers is based on the data directly available in the marketplace. Another model enables classifying driving behaviors relevant to car insurance companies. The Cross-CPP project gives cyber-physical product users, individual or corporate data owners, a full control on the use of their data. They can choose whether or not to share the data with third parties and have contractual guarantees that the data will be only used in the way to which they explicitly provided their consent. A key part of the contract and consent management takes place at the link between the company backend and data owners. The data provider is responsible for ensuring that the data collection process is in consent with user intentions. The company backend has to handle the consent of each particular data owner. To guarantee the transparency of the data usage, the system provides mechanisms for the data owners to be always aware of what entity is using which data for what purpose, even for the usage of anonymized data by a service provider. The privacy preservation considerations are embodied into operational interactions between the data owner and respective shareholders of the overall Cross-CPP ecosystem and are part of the project solution. Even if a data owner agreed to provide his or her data through the data marketplace, the data use for a particular purpose is determined by accepting a data request offer defined by a service provider. Data providers can examine details of particular offers and the way the data would be provided and decide whether they correspond to the intended data sharing. The screencast shows how the data providers can accept data access offers created by service providers and how they can terminate formerly accepted contracts. The data wallet contains the list of all the published offers. The user can review the channels that are requested and other parameters of the proposed offer. They can also consider the intended use of the data. Finally, the user decides whether to accept a particular offer or not. The data wallet also enables inspecting the list of previously accepted offers. If the user decides that the data should not be provided to a particular service anymore, he or she can terminate the data provision contract from the list as well. The contract remains in the list of previously accepted offers with an indication of the termination date. The security objectives of the Cross-CPP project arise from marketplace challenges, including support for dynamically changing confidentiality, privacy, and intellectual property constraints, as well as ethical requirements, which we refer to collectively as security constraints. There is a need to assure optimal management of security constraints depending upon the actual context under which data streams are used or generated. This demands that services can be adapted to the current needs of the user according to the security constraints and conditions relevant to the current context of the user, the device, or client application. A definitive new requirement for Cross-CPP is context sensitivity security with the ability to adapt the policy at runtime according to the context. Here we see the implementation of the context-sensitive security design paradigm in the CPP Big Data Marketplace. At the heart of context-sensitive security is the lightweight next-generation access control components developed by the Open Group. A declarative policy language based on the NGAC industry standard policy framework is used to express an access control policy for data, devices, users, and other resources within the CPP Big Data Marketplace. A policy tool is used to develop and test security policies expressed in the language. One or more policies may be loaded into the policy server and combined to elaborate complex security policies. Policy enforcement points along the resource access path mediate access to protected resources by client applications. Upon receiving a request from a client application, the policy enforcement point asks the policy server for a policy decision according to the current security policies. The server replies with a grant or deny response and the policy enforcement point acts accordingly on the client request. A definitive new requirement for Cross-CPP security is the ability to adapt the policy at runtime according to the context. This is accomplished through an interface with the Cross-CPP context monitoring and extraction module that provides a context mapping for policy rules and the ability to modify policies based on context changes. To meet the marketplace challenges, innovative context-sensitive security components allow the definition and enforcement of policies for data access. These policies can range from global platform-level policies, to policies restricting access to particular items of data in a dynamic way. The key security innovations include fine-grained end-to-end security policies capable of protecting data at multiple levels in a distributed system. Multiple security policies and composed security policies to factor complex policies into portions that are easier to administer. Security policies conditioned on dynamic context. A policy is interpreted according to context variable values. Event response language for dynamic policy change predefines policy changes to occur based on context change notifications. Scalable for big data and many clients, permitting policy data objects and users to be added or removed dynamically.